Hi, I'm Carol Holmberg. I'm the planetary manager at the Museum of York County here in Rock Hill, South Carolina. And welcome to our National Chemistry Week 2021 presentation. This year's National Chemistry Week theme is all about reaction rates. Faster, slow, chemistry makes it go. And in this presentation, you will learn all about what makes reactions occur faster or slower. And you'll see some activities that you can do at home. Are you ready? Let's get started. I wanted to start out with a very fast reaction, one that could potentially save a life, that of automobile airbags. Now, how do airbags inflate? Not with compressed air like a balloon. That's much too slow. Your typical car crash happens in just a fraction of a second. So airbags need to inflate in about 30 milliseconds. That is about 1/3 of the time it takes for you to blink your eyes. It's very fast. When an airbag inflates, there is a heating sensor that heats up a chemical, usually sodium azide, which is very sensitive to change in temperatures, and that sodium azide will inflate the airbag. It releases nitrogen gas, the main chemical that's in air. And you don't want the airbag fully inflated when you hit it, because it would be like hitting a wall or the dashboard. Instead, the thing has to be inflated and on its way back to deflating, so you have a bit of a cushion. You will see more about airbags and how they work in this next video segment produced by the American Chemical Society and used with permission.
Normally, something blowing up in your face is definitely bad. But right about now, this chemical reaction could very well save your life. It takes 50 milliseconds for you to hit the steering wheel in a crash. Everything we're about to tell you goes down even faster. Your car has to be able to detect when a potentially deadly crash is happening. You don't want your airbag deploying every time you hit a pothole or get in a fender bender. Your car has an accelerometer, several actually in case one fails or goes off by mistake, that detects sudden, rapid changes in velocity. In one model, a ball bearing is normally held in place by a magnet, but in a crash, it comes flying free, and it flies right into an electrical circuit that tells the car's computer to deploy the airbags. Airbags don't just fill with gas like a balloon blowing up. That would be way too slow. The gas that fills airbags is actually produced by a chemical reaction. The classic example is sodium azide, which is stable until it's heated. In a crash, a small explosive or heating element called a squib goes off and ignites the sodium azide, which decomposes quickly to nitrogen gas and sodium metal. That sodium metal could react with water in the air to produce corrosive sodium hydroxide, so airbag manufacturers include some other compounds to react it into sodium oxide and alkaline silicate instead. By the way, the technology we described is a little old school. Nowadays, most frontal airbags are actually inflated with guanidine nitrate, but it works on the same principle as sodium azide. You're creating a lot of nitrogen gas. And accelerometers have changed with the times too. They're a little more sophisticated than the ball bearing thing. Meanwhile, the nitrogen gas is totally harmless, being the main ingredient in, air. Just a small handful of sodium azide can produce 67 liters of nitrogen. And that volume of gas creates enough pressure to fill the airbag in less than 40 milliseconds. So, quick first law refresher, an object in motion stays in motion. So when your car hits something, it stops, but your body keeps moving forward. And if it keeps moving forward right into the steering wheel or dashboard, that's bad news for you. So the airbag is there to slow you down more gradually than a steering wheel would. But this rapidly inflating cushion isn't actually pillowy soft. The front face of the airbag moves toward you at between 150 and 250 miles per hour. And if you were to hit it while it was still inflating, that might be almost as bad as hitting the steering wheel. To properly slow you down, an airbag has to have blown up already when you hit it. So that means the accelerometer detects the crash, the squib ignites the sodium azide, the nitrogen gas is produced, and in 50 milliseconds, it's already blown up in your face and started to wind down. Between 1987 and 2015, frontal airbags saved 44,869 lives. That's a summer evening at Dodger Stadium's worth of people, and a lot of people around to cheer thanks to one chemical reaction and some ingenious physics. Thanks for watching, and remember to drive safe. This explosion could save your life, but it's still better if it doesn't have to happen. If you like this video, help us make more by clicking here to subscribe and then hitting the bell to get notifications. Seriously, do it. Also, if you're curious about the Takata airbag recall, we threw a link in the description so you can check to see if your car is affected. Thanks for watching, and we'll see you next week.
Okay, so next we are building a battery. We're using chemicals to make electricity. And what I've got are some felt washers, and they have been soaking in vinegar. They need to soak for at least a half an hour. These have been soaking a little bit more. And some copper washers and some zinc washers. And you can find those at a hardware store. And I've got this little plexi stack so I can stack them. And what we are recreating is the very first battery. It's called a voltaic pile or a voltaic stack. And it was created first by Alessandro Volta in the year 1800. And so first we take a copper washer with a little bit of wire, and then we put a little felt washer that has been soaking in vinegar, and then we have a zinc washer, and that's one stack. We're going to have to do a few stacks, at least 2 or 3, to get enough volts, they're named after Volta, to light up our little light. Batteries work the same way. 3 stacks is about the same as a AA battery, 1.5 volts. And the last washer needs a wire attached to it. So the idea is that electrons, which are the part that flow in an electric circuit, they flow from the copper washer at the bottom, and they flow into the light, and then they flow into the zinc washer at the top, and that creates a circuit. And then sometimes, if you can't see it, if you press down on the stack, that helps as well. Well, that's pretty much it, and you can make your own little batteries. Can you imagine not having a battery for your cell phone, being stuck with landlines, or all the other things that batteries do for us? Well, this activity is called slowing apple brownie. Have you ever taken and eaten half an apple and saved the other half for later, and then noticed that it's turned a yucky brown? Bananas, the peel turns brown. Pears also turn brown. First, you need to cut the apple. And if you don't have apples, you could use pear. I'm going to put in the control. We're not going to do anything to it. And we are going to prick the rest of the slices. And that is going to damage even more cells. Here's a slice that we'll put in with the lemon juice, and one for the vinegar, or the salt water. Here's for sugar water. There's the lemon juice, and here's the vinegar. we have sugar, and I'll add some water, and then salt. And you can look at the controls and see that they're already browning a little bit where they were cut. And you can see that the pricks of the fork make it even browner. Here's the lemon juice, vinegar, the salt water, and the sugar water. And we are going to come back in 10 minutes and see if they've browned a little bit more. Just the apple slice that I sliced and the one that I pricked. And you can see that, especially in the pricked areas, it has turned brown. Here's the lemon juice. And lemon juice is acidic. It stopped some browning, but did not eliminate it. Here's the vinegar, the salt water, sugar water. What would you use? Think about that. That might be a little acidic and maybe stop the apples from browning, or would you just put up with some browned apples? Next activity that we have is Mentos and Soda. And for this, we're gonna show you a video courtesy of the Oregon Museum of Science and Industry, OMSI, used by permission. You can try this at home. We've got a tube of fruit Mentos. You can use either fruit or mint Mentos. And the idea is to insert it in soda, in a 2-liter bottle of soda, and it makes the soda fountain up and kind of explode. This reaction is quite rapid and dramatic. Now, as you will see in the video, diet soda works the best. Appalachian State University actually a few years ago had a class look at why the reaction was so spectacular. It turns out that Mentos have a very rough surface, a big surface area, as this image shows, taken through a microscope to show the roughness and dimpleness of fruit Mentos. Another variable is that the soda needs to have gum arabic, which kind of coats everything. And Mentos work well because they have a rough surface and are dense and sink rapidly. And the reaction creates carbon dioxide bubbles, which are present in the soda, and you will see a spectacular effect as this video shows.
Today we're going to talk about Mentos and Soda. You've seen this reaction before. It's awesome. Now we're going to talk about the science behind it. We're going to look at how different factors affect the way that soda explodes. As you probably know, this is a reaction based on carbon dioxide gas. When you drop the Mentos into the soda, all of the carbon dioxide bubbles all come out of the soda all at once. It foams up and shoots out of the bottle. You can combine this with your favorite dry ice demonstrations. You can make quarters scream, put out fires, and make a liquid change from neutral to acidic. Now, it turns out that the acidic quality of carbonated water is delicious to us, which is why we put bubbles of carbon dioxide gas into our beverages, and that's the connection between dry ice and this demonstration. Different kinds of soda also react differently to the Mentos. As the Mythbusters showed us, different ingredients in the soda enhance the reaction. So this is just plain carbonated water without any additives except the carbon dioxide. And that's not much of a reaction. When we add in flavoring and sugar, it gets a little bit more exciting. But we know that if we add the diet sweeteners, then it gets a lot more energetic. And it gets really good when you add in caffeine. And And as hundreds of middle school science projects have shown, the most explosive soda to combine with Mentos is Diet Dr. Pepper. This is also a great demonstration about how amounts of surface area in a substance can change the way it behaves. The reason that Mentos make all of the bubbles come out of the soda is because Mentos are microscopically rough. They're covered with millions of tiny pits and bumps, places where the bubbles can form. To show that, we're going to put other substances with surface area into the soda. This bottle's getting Mentos, this one's getting sand, this one's getting iron filings, little tiny bits of iron. And to show you that it's surface area, we're going to drop an iron bolt into this bottle. It's iron, but it's one big chunk instead of lots of little pieces. So, here we go. Iron. Oh. Go down, iron filings. Sand and Mentos. Another factor that has a big impact on how much the soda explodes is the temperature of the soda. This is because temperature affects how much carbon dioxide you can dissolve in the liquid. So here we go. This bottle has been chilled in the refrigerator. This bottle's room temperature, and this bottle has been sitting in hot tap water for the last hour. Cold. Room temperature. Hot.
First of all, you take some warm water. 110 degrees Fahrenheit is the perfect temperature. And from that could be either instant dry yeast or we have packaged dry yeast at home, about 2 teaspoons. And mix it in with the water, and you'll know that it's at a proper temperature when the yeast starts to foam. If it doesn't do that, the yeast is dead. And the yeast is what releases the carbon dioxide, and it is the enzyme, the catalyst that you need. And once you combine those and a little bit of sugar to kind of encourage the yeast, and you're going to have to knead it to form the gluten strands. Then we let it rise until it's about double in size. This recipe only needs to be risen once. And then you're going to break the dough. You're going to have to roll or squeeze, and then you're going to have to shape the pretzels. You're going to have to drop each pretzel in boiling water. Each one just a minute or two, turn it over. It's boiling water and a little bit of baking soda, and then sprinkle each one with salt and put in a preheated oven, and then give it about 12 minutes until the pretzels brown, and you are ready to go. And I hope that you find this fun and easy to do as well. You could make pretzels, so you could make lots of baked goods without yeast, but yeast hastens the reaction. So this is a good and tasty way of investigating reaction. Time for one of my favorite reactions called rocket reactions. And for this one, you need 2 things that are found in the kitchen, baking soda, and you might not have it, but you can find it in the grocery store, citric acid. I also have some Alka-Seltzer tablets to try. The hardest thing to get of everything are the film canisters. We don't have film in canisters much anymore, but scientific places on the internet should have them. Let me take a film canister with taking a scoop of the baking soda, and then I'm going to take a scoop of the citric acid, and you can combine a bunch of each in a beaker, equal amounts, and label it rocket fuel. And then I'm gonna add a pipette of water, a few drops of water. And the idea is to add a few drops and then count to 3 before you cap it. Turn it upside down and wait. And we have success. I wanted to try this a little bit differently now. I wanted to use the tab of Alka-Seltzer. And then we're going to take an eyedropper full of the water. We're going to put it in. And remember, you don't have to wait the 3 seconds now. You just have to seal it up and put it upside down, and you wait. Well, thank you for coming to our National Chemistry Week program. And as a thank you for watching, I have a treat for you. We have several hundred of these National Chemistry Week celebrating chemistry brochures. You're welcome to come to the museum and pick one up while supplies last. It's got wonderful things for you about reaction rates, and the apple experiment is in there, as well as 2 new experiments, one with pop rocks and one with glow sticks that you are welcome to do at home, as well as lots of exciting information. And we also have a roll of National Chemistry Week stickers, and they should be available for the rest of the month. And I hope that you come to the museum and ask any questions that you might have, and enjoy this beautiful magazine brochure as well as a sticker. Thank you.